Hello everybody, welcome to Blue Marble Science. Imagine hearing this. Good morning ladies and gentlemen, I'm the Quantum Eraser and I'll be your pilot today. Oh yeah, that's a two-screamer alright. You gotta figure that there's gotta be some topic out there that John the Quantum Eraser would avoid, realizing he doesn't have any expertise. Unfortunately, aviation isn't it. Oh dear. Warning, facial injury and monitor damage are likely, so get out those oven mitts, push that monitor back out of punching range, and Gladys, I found another jackass for you to play with. What do you mean you don't think he's a real jackass? He's one of the better jackasses you'll ever run across. Ladies and gentlemen, please remain seated with your seatbelts fastened and your tray tables in the full upright and locked position as we get ready to light this dumpster fire and have some fun.
Well, thank you. Are we going to start already?
Yeah, definitely. Let's get straight into it. There's people out there keen to see flat earth proof.
No chit chat. I'm liking it. All right. Well, first off, these proofs are not scientific evidences. Why? Well, what have we talked about for the past 8 months? Is the Earth flat or is the Earth a sphere? Well, those are what is questions. The scientific method only deals with cause and effect, how I question. So this is off the table with scientific evidence. So like I said, it's not as sexy as scientific evidence, but it's got teeth. So where do we want to begin? Let's start with, I know where to start. I've given this presentation to 3 astrophysicists, a physics teacher, we all know who that is. And you know what I've gotten back besides name calling from the first 2 astrophysicists? Zippo, nada, nothing. I also, as we are always challenged by the Globetards, is to give them, give me your proofs of the flat Earth. So obviously I got that thousands of times. And a few months ago, one of the Baltards, challenged me with it. And I said, no problem. I said, here you go. Here's the video of the last time we did these proofs. And just, check it out at your leisure and get back with me, right? So a week passed, and I challenged the person back again. I said, well, have you watched them? The answer was, and we'll keep all names out of this to protect the guilty, I don't watch scary movies. So that's where we're at here. These people are not going to watch this because it's over. That's it. So let's begin. So let's define drop, because of the first 2 proofs, this is going to become critical. And I don't know, like I said before, we talked about this before. It seems that the Baltard spinning space monkeys have forgotten this. It's one of the critical, crucial tenets of their religion. It's vertical drop. Every point along a tangent from your feet drops. That is, vertical drops away from you at 8 inches per mile squared. Right? It's almost shocking. Some people, you say this and they get that deer in the headlights look, like they ever heard of it. I mean, hello. So, and to say dropping vertical or vertically, it's kind of painfully redundant, right? Well, what other way are you going to drop? So from dictionary.com, let's take a look at this. Drop, to fall vertically, have an abrupt descent. From Oxford Dictionary's drop, let or make something fall vertically. So height, altitude, elevation, mean vertical distance. Vertical, elevation, vertical drop. I don't know why we have to keep on going over this, but we do.
Okay, Captain Numbnuts, before you get completely crazy, let's make sure we understand the true definition of elevation. You see the little airplane down here in the right-hand corner? Let's read this. The elevation of a geographic location is its height above or below a fixed reference point, most commonly a reference geoid, a mathematical model of the Earth's sea level as an equipotential gravitational surface. QE, it is the height above mean sea level. That, by definition, is what we use when we fly airplanes.
Now, the first proof. Flight. This is the one I always lead out with when I'm talking to people. Why? Because it's the easiest. Most people have taken flights before, right? An incoherent second grader can reconcile this quite quickly. By the way, you'll never see this. This shouldn't happen on a sphere Earth. This plane is level. Shouldn't happen. So it's already, we can stop right here. Nah, we'll continue.
No, jackass, you really should stop right there while you've only just mildly embarrassed yourself. But you're not going to do that, are you? Of course not. You got 4 feet, you might as well put all of them in your mouth.
So, since the Earth is, as we're told, a sphere 25,000 miles in circumference, radius 3959 miles, then pilots traveling for 1 hour at a typical cruising speed of 500 miles per hour to simply maintain altitude would constantly have to adjust their altitude downwards, to compensate for the curvature and descend on average 2,789 feet every single minute.
QE, why is it every flat earther messes this up? Are you guys just that desperate to hang on to your narrative? Why can't you understand that airplanes don't know where the ground is? They don't care where the ground is. They only know the density of the mass of air that they're flying in. Contrary to what you think, the airplane does not start at some altitude and then suddenly go whizzing off into outer space. That's ridiculous. It stays at the altitude above mean sea level that it was trimmed to fly at. Good grief. It looks like that. Then it looks like that. Airplanes don't climb or descend unless we make them do that, you dodo.
How'd we get there? Well, how many miles of vertical drop that's geometric must be negotiated over a distance of 500 miles on a ball with a circumference of 25,000 miles? Answer, 31.7 miles. How many feet are in 31.7 miles? Answer, 167,376 feet. So, 167,376 feet of vertical drop must be negotiated over 500 miles on Earth. Number one, real world. I'm traveling by commercial flight from Pittsburgh to Atlanta, Georgia for the Super Bowl. Approximate distance, 500 miles. Typical cruising speed, 500 miles per hour. So 500-mile distance at 500 miles per hour. Travel time equals 1 hour. So how many feet of vertical drop per minute on average needs to be negotiated on my trip? Total feet, vertical drop over 500 miles. Again, 167,376 feet. Travel time is 1 hour. It's a simple calculation. 167,376 feet divided by 60 minutes. Answer, 2,789.6 feet. Vertical drop per minute average must be negotiated on my trip. Does this happen? No. The nose on a plane on a typical flight would never get above horizontal, save for takeoff. The sphere is a stone cold fairy tale. B, let's try another example. How many miles of vertical drop, that's geometric, must be negotiated over a distance of 1,000 miles on a ball with a circumference of 25,000 miles? Answer, 128.3 miles. How many feet are in 128.3 miles? Answer, 600,707,424 feet. So 600,777 or 600,077,424 feet of vertical drop must be negotiated over 1,000 miles on Earth.
Way to go, lame brain. You want to try that again?
How many feet are in 128.3 miles? Answer, 600,707,424 feet. So 600,777 or 600,077, 424 feet of vertical drop must be negotiated over 1,000 miles on Earth.
And you called me an uneducated hillbilly.
How many feet are in 128.3 miles? Answer, 600,707, 424 feet. So 600,777 or 600,077, 424 feet of vertical drop must be negotiated over 1,000 miles on Earth.
You're despicable.
Another real world example. I'm traveling by commercial plane from Pittsburgh to Dallas. Approximate distance, 1,000 miles. Typical cruising speed, 500 miles per hour. So 1,000-mile distance at 500 miles per hour. Travel time of 2 hours equals 120 minutes. So question, how many feet of vertical drop per minute on average needs to be negotiated on my trip? Total feet vertical drop over 1,000 miles is 167,376 feet. Travel time, 2 hours. Simple calc. 600,077, 424 feet divided by 120 minutes. Answer, 5,645 feet of vertical drop over a mile drop per minute average must be negotiated by the plane on my trip. It's just that simple. Does this happen? No, of course it doesn't. Alice in Wonderland is more tenable than the honorable ball-tard spinning space monkey religion. The prosecution rests. Simple. You live in a fairy tale. The end.
Well, thank goodness that's over with. I did an entire video on why airplanes don't dip their nose as they fly along to stay at their desired altitude, and I'll put a link to that in the comments. Let me run through it really quickly. It'll only take a couple of minutes. An airplane is controllable around all three axes. As you see in the diagram, we have a longitudinal axis that runs through the center line of the airplane, right through the center of gravity. And as rotation around that axis is what we call a roll. And that's what we use to bank the airplane, bank the wings, and turn the plane. There's a lateral axis that runs through parallel to the wing, again passing through the center of gravity. The rotation around that axis is pitch. That controls the pitch of the wing and the angle of attack of the wing. The third axis is the vertical axis, again running right through the center of gravity of the airplane. Rotation around that axis is what we call yaw. We use that to assist us as we're turning the airplane to keep the turn coordinated, and we also use it to keep the nose pointed in straight down the runway when we're taking off and landing. Airplanes only know four forces that are acting on them. They know the weight of the plane, they know the lift of the wing that the wing is creating, it knows the thrust that the engine or engines are creating, and it knows the drag that is resulting from the lift that's being produced and parasitic drag just from friction of the air. In level unaccelerated flight, only two things have to be true. The lift has to equal the weight, and the thrust has to equal the drag. If those two things are true, the plane is in level unaccelerated flight, and it will stay in level unaccelerated flight until we change something. And by level, I mean at the altitude the plane is trimmed for. Here's a little diagram, shows a little Cessna, looks like maybe a 182. And you can see the angle of attack shown in the diagram above. Lift is generated by airflow over and under the wing, and it depends on the speed of the air and the density of the air. The more dense the air is, the more lift it produces. The less dense it is, the less lift it produces for a given angle of attack. The airplane stays at an altitude where the density of the air produces the lift required to exactly match the plane's weight. So, if I climb in this airplane up to 10,000 feet and then I adjust this trim tab on the back of the tail to maintain level flight without touching the controls, the plane will simply stay at that altitude. In other words, at that air density level, which is consistent with mean sea level, with respect to mean sea level, I should say. And it will just remain there until something changes. As we fly along and burn off some fuel and the plane gets lighter, it may want to climb a little bit. If the barometric pressure changes, barometric pressure drops, it may want to descend a little bit. So we have to make a few minor adjustments, but we make no adjustment for the curvature of the Earth. That's the bottom line to it. That's pretty much the end of it. Hey, thanks for watching. Be sure to let Quantum Eraser know what you think. If you ever get on an airplane and you see him in the front seat of the plane, get off the airplane. Don't forget to like and subscribe. Just push the little button down there and we'll see you guys on the next one. Hey, Gladys, we're out of here.